Welcome to the Valve Studio. My journey to Tonehenge continues. Tonight we're taking a sidestep. We're going to have a very in-depth technical discussion about embedded firmware and performance issues and what I ended up finding when I was trying to get my jog wheel to be smooth. If you're interested in this, continue watching. If not, please hit the stop here. Don't continue, and just have a great day. All right, let's get into some detail here. So my implementation is a WorkB 1010 that's running a port of GRBL over on a PSOC 5, and I've added some additional things for my operator interface. And what we were seeing a couple videos ago when I was kind of moving back and forth in X was a disruption in motion, and I eventually isolated that down to software issues. It wasn't a mechanical issue. It wasn't hardware. It wasn't noise. It wasn't signaling. It wasn't any of that. It was something I had done in the software. So I'm going to go over how I found that and how I fixed it. I'm going to try to make this as short as possible because this is like my 20th take. All right, here we go. So I isolated it down to this thing right here. This is my LCD display that's on the operator interface. I'll show you that here. So it's this little display, and when I basically disabled that, updates to that display, everything was smooth as glass. Once I turn it back on, we kind of get that clump again, that clunk. That clunk, clunk, clunk. Now that clunk, clunk, clunk comes from when the way the GRBL works, it's interrupt driven, but the thing that the mechanism that feeds the interrupt on what to do when at interrupt time is called the planner. The planner figures out how many steps need to be in the next step of the plan, and looking back one more step, we have the parser, which takes your G code, parses that, formats it up, loads it into the planner, and then the planner comes through and figures out the steps. And ultimately, if you starve the planner, the interrupt handler comes through and doesn't see that there's anything to do in this interrupt cycle, and just doesn't do anything, and that results in a stop in motion. And you could not see that when I'm executing the jogs, but you could hear it because that little bit of a stop, clunk, 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 that's what I was experiencing. And I isolated it down to doing the refresh of this screen here, which is an I2C display. So we will talk about this here. So the traditional way of writing this display out is setting the cursor and then basically pumping characters out to the display after you've set the cursor. So if we want to set X here, we set the cursor to this position here. We convert to double, which is the value of where we are in the XY coordinate space. And then we convert that to a string, and then we pump that string out to the display, and then we're done with that, and then we move on to the next position, and we do a bunch. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pieces of information. This last line here is the last line that was successfully parsed and is in the planner now in the planning stage. So I measured that. I measured the I2C time it took to actually update this screen. So I have this display here. So I put my logic analyzer on the PSOC control lines, the data in the control line, the clock line, and I measured out a full refresh cycle takes this number here, this delta X, almost 63 milliseconds, which in the CPU world, is pretty long. And what's curious was why are there gaps here? Because if you're writing it out, you don't need any gaps. Just pump out all the data. All right, so I zoomed in on this. So I came in and I zoomed in on this, and I see that what we're seeing is we see this one, then we see this one, then this one, then there's the delay. They come in groups of 3 for some reason. And then this amount of traffic right here is a command. In the I2C world, it's the start condition, the address with the read-write bit, and then the data, and then the stop condition. So we're seeing the address and a byte, the address and a byte, the address and a byte. Okay. So basically, let's say you're going to write one display. So I had to go through and I had to figure out something else. So I went and I looked at the hardware design for my display. Now my display is a LCD display, and it uses a Hitachi HD 4470, which is a really old controller chip for displays. And I found this app note from a company called Systronics, and it was written 18 years ago. It's a little easier to read than the Hitachi datasheet. Kind of explains things a little bit in more detail. Then I looked at the schematic, and I determined that this display has been running in 4-bit mode, which means that the controller, the I2C controller that I have, I forgot a step. You got the LCD display, then I have a thing called an I2C backpack on the back of the display. That backpack basically exposes the lines on the display, but it exposes it through an I2C interface. So it's a little cryptic to write to it, but you can manipulate the digital lines going into the display and send out the commands that you need to send out. But you're running 4-bit mode, so that means that every byte you send, you have to split it into the upper nibble and send those 4, and then you have to send the lower 4. And so every byte gets split into 2, and then from there you send out those 2, and that's what you're actually seeing in this thing here, is that you're seeing the address, and this is probably the high 4 bits, and then this is the address, and then the low 4 bits, and the address and the high 4 bits. It's something like that. So every byte you send, the code was sending out three bytes to get a single byte sent out. So I looked at the code itself, and let me switch over to here. So this is over in the PSOC Creator. I downloaded this LCD code from somebody else's project that ported one of these libraries over to PSOC, and it works. It goes in here as it mentions the 4-bit mode, and it does all this setup sequence correctly, and he has a bunch of helper functions in here like home, clear, set the cursor, turn off the display, turn it on, turn off the cursor, turn it on, don't blink. These types of things are pretty common for these device drivers. And then if you want to send a byte out, it's got to come down and split it. So it does this high bit and a low bit, and it sends the high one and the low one. And then that one goes out and does this, and it calls another function, and it calls another function, and it calls another function. So the call tree to actually write out one individual byte is probably 10 calls deep to get down to this last final function here. And it sends a start condition with the address, and it's going to send out the zero bit, which means I'm going to do a write, and then it does the master write byte. So it does the 1 byte, and then it sends a stop condition. So if we look over, here we go. If we look at this, that's what this is going on here. This is the execution of that last function is right here. So this is pretty inefficient. That's why we're seeing a 60 millisecond duration to send out the 80 characters that are needed. All right, well, I'm going to figure out, I'll got to do a little better than that. So we'll show you what I ended up working on. I ended up working on a different approach. So I used a off-screen buffer technique. This is the way a lot of display drivers work, is they have an off-screen buffer, and then they update this off-screen buffer, and then periodically some like a mem copy routine comes through and grabs out this and pumps it into the display memory, and that sets the refresh rate. So you write into this one, and then the next refresh cycle you go do a mem copy, and that mem copy happens pretty quickly. Over on I2C, we have an option that I'm going to use that's a PSOC component from the library that allows you to not write it in this byte by byte fashion, because during that time, during this whole 63 milliseconds, the CPU is being completely monopolistic. It's not allowing basically the planner to come through and plan these next operations. And that's a really long time, and if you're doing a lot of really small steps, which is what really fine CNC G-code work are going to be implementing, so you can't do it this way. All right, let's go back over to my thing here. So I don't do it this way either. But what I do is I create this buffer, and I write all my data into the buffer, and then I periodically come through and flush that buffer out onto the display. And that buffer is actually created using one big giant printf statement. So if we come over and look at it, it's right here. Oops, let me switch over to here. It's all done in one big printf statement. So I wrote out this printf statement basically writes all 80 characters all into the status array, which is a 80 character long character string. And then when I was looking over the data sheet, this data sheet here talks about the way that the internal memory is laid out in the. Well, I don't need to show you that. Basically in the display here, there's basically 80 characters of RAM, and whatever we put in those 80 characters of RAM is what comes up on the display. So I wrote a little project in the baby steps folder called, probably LCD 2040 or something like that, 2004. So if we look at the RAM addresses, it works out that this is 0, and then this goes out to 19, and then number 20 is not this position here. It's this position here. So this is 20 out to 39, and then 40 is this one, and goes to here, and then this one down here is 15. It's 60 out to 79. So I have to write this into my off-screen buffer in this order, and then periodically come through and write it. But while I was writing that little baby step program, I've discovered I can't write all 80 bytes all at once. So I have to write them in 40 byte chunks, and so I have to write the first 40, which are lines 1 and line 3, and then I have to wait a certain amount of time. Then I can write the other 40 characters, which is line 2 and line 4. Okay, so that small amount of time that you have to wait determined to be about 12 microseconds, and so but you still got to do it. You can't just write them all out. Okay, that's just experimentation on working with the hardware. So what did I get? doing it that way, I got this. So this is my implementation of doing a buffer write. It took 9 milliseconds to do the entire buffer write. Now, the PSOC has a component that implements a buffer write function. So I can basically form up this output buffer, this off-screen buffer, and then call this function to a pointer to my first memory address and how long I want to write. And the internal guts of the PSOC handle all the byte-to-byte manipulations with the internal I2C controller. And it does that through an interrupt handler. If you're going to write this in a pulled fashion, you send a byte, then you have to wait for it to get completely transmitted. Then you send the next byte, so you copy it into the I2C controller. You send the next byte and wait for the transmission to complete and do it again. The PSOC implementation actually implements an interrupt handler, so I call this one time with my pointer and my address, my length, and then it takes over and writes all this out. So during this 9 milliseconds of time, I'm not waiting a loop. In fact, I can go back over and execute the planner or whatever that I want to do. So if we switch back over to our screen here, so the kind of the question is, how long does it take to do this printf statement here? In fact, there's a lot of setup involved in getting this to work right, because we have to come through and get the position that we're currently in, which is all this stuff up here, because we have these work coordinate systems and machine positions and all that. And then if we're in metric, we got to convert it over to millimeters, and then this home function basically sets the RAM pointer internal in the display back to 0. Then I do this sprintf, which copies everything into status with the right line orientation for that discontinuity at character 40. And then this little guy down here, well, we'll talk about him in a minute. So how long does this whole thing take? Because ultimately we get down to this one function here. This is called master write buffer. And we tell it what the display address is and the buffer. This is the address of my buffer and how many I'm going to write. I'm going to write 160. We'll talk about that in a minute. And then the characters. I don't think that 160 is right. Okay. Anyway, so we write that out. Okay. And we go. Why is that? That shouldn't be 160 there. That should be 80. Anyway, let's continue. I don't want to go into too many details here. Okay, so how long does this all take to get set up? So I have a plot for that. I came in over here and I can run my screen here. If we look at this thing here, I added an extra bit, output bit, and I basically, this duration of this is all the extra setup to write the string. And so this is 3 milliseconds. So it takes my code 3 milliseconds to completely write the off-screen buffer, and then I just call that function, and then the microprocessor takes over, and it's interrupt driven at this point, so it's free to go off and do other computations. So now I'm down to 3 milliseconds. Well, that wasn't really fast enough. The way that I ended up writing, so let me go back to my other screen here. So once we get the buffer written, once we get all the character buffer written, we got to split it. Remember, because we're running in 4-bit mode. So my first my first attempt at writing this was to have a for loop here based on how long we want to go, and then I do a bunch of operations, and I increment my index counter, and I do a bunch of other things, and that's where this 3 milliseconds comes from. But then I came back later and I rewrote this using pointers. I wrote this function, this little bit of code right here, using pointers, and that resulted in me reducing this 3 milliseconds down to this one here using a pointer. I got it down to 1.3 milliseconds. All right, so what I got down to is I took a routine that was hogging basically the CPU for 63 milliseconds, and I got it down to 1.3 milliseconds. And when it's sitting at 1.3 milliseconds, we don't interrupt the planner. The planner can go off and execute its own thing, and we don't have interruption in motion, and that's what makes the jog wheel actually work pretty well. And so when I'm running a G-code file, I don't hear those clumps or disruptions in motion any longer. So that's how I ended up finding all this, and I used some functionality that the PSOC implemented, and I read the data sheet for the device, the display, and then I modified my code, and the 3 milliseconds was still not enough, and I looked at that and implemented in pointers, and a lot of people despise C for this whole operation, this whole loop that I wrote here, because it's basically prone to this loop right here is basically prone to a lot of errors in writing it. You could overwrite memory and do all the things that other people don't use C for. That's this loop here. But if you really want to get high performance out of your systems, you have to go down to this level and learn how to write it like this. Okay. With all this changes here, I'm able to do my refresh rate of my LCD display 10 times a second, which is right on the edge of the LCD latency on the way that the crystals change in the liquid crystal itself. I can't do it any faster. I'd like to do it faster, but liquid crystal display at that point is not the right technology to actually have high refresh rates. You need to move to a LED or OLED display to do that. If I did this all over again, I wouldn't use one of these little displays. I'd go ahead and fork out some cash and get an SPI display. And even though I'm running I2C at 400 kilobits per second, which is pretty fast, I don't see much of a change. Well, I certainly don't see much of a change in this 1.3 number over here, because that's CPU time, that's CPU execution time, that's not the bit transfer rate. I did measure this at 1,000 kilobits per second versus 400 kilobits, and the incremental change wasn't even worth it, and so I don't bother running it that fast. What else was I going to say? I could make this faster down here, but I don't really need to, because the frame rate is, I don't need to do it. I'm using up this little bit of time, and the planner doesn't seem to mind. All right, well, it's a long explanation. Hope you got something out of it. And I hope that answers some people's questions about some performance issues I found and how I isolated them and how I resolved them. Okay. Thanks for watching. This is the Valve Studio.